Swayam Prabha. Digital India. Educated India.
So it is my pleasure to be here, and I hope that you could be interested in energy harvesting. So as Professor Ali Sheikh Farooq Ali told, we are working long time on energy harvesting, not only on energy harvesting, but also some other nonlinear systems, dynamics. However, today there is a plan that I present some linear harvesters, and of course these linear harvesters are not used so much, but they are good to understand what are the rules and how to design such systems, and then there would be also some short introduction at the end in the second lecture. Today I would have some introduction also to nonlinear dynamics, telling preliminary what is important in this with nonlinearities, and nonlinear dynamics would be presented also tomorrow. So today it is like there would be preliminary introduction, and in the beginning I want to show you some preliminary information about the electromagnetic and piezoelectric harvesters. So let me start. If I remember, Professor Sheikh Farooq Ali gave some introduction to the field, gave some introduction already to the field. So I want to summarize the nonlinear energy harvesters, and then the first is what is the concept? The concept is that we have to find some if we want to design such a device, we need to find some rule which could be used to change the energy, mechanical energy, into electrical energy. And there are many possibilities, and one of the possibility is to use electromagnetic, another one is piezoelectric, but there are some more options, and for example electrostatic, there is some possibility to change also the energy, mechanical energy to electrical energy. You can imagine that you can have a capacitor which is which size is changing, the distance between the electrodes is moving. Yeah, so this is like a concept for electrostatic. And the difference between, for example, electromagnetic and piezoelectric is that we can scale differently. For example, for piezoelectric, we can scale down to smaller size than electromagnetic. Electromagnetic, it is the device which needs some scale of at least of 10 centimeters. Yeah, some 5, maybe 10 centimeters. You need such a length to place the electromagnetic device. However, piezoelectric could be scaled to even to some smaller size, like 1 centimeter or maybe even smaller, and electrostatic could be very small, so could be like MEMS. Even piezoelectric could be scaled to such small size, but it is more difficult. So electrostatic would be more precise solution in a smaller scale, and then if you go to electromagnetic, then there is such a Faraday law Faraday law is that you have some magnetic flux which is variable in time, and if you have such a flux, then you can induce voltage, which is the derivative of a flux. So you have time derivative of a flux like a voltage, and then it is important to just to look for some. If you have such a flux, then you have also current. So this is the current is induced in the electrical circuit, and you have electromotive force as well. So this is you remember that some electromagnetic motors are working using this rule. However, this is the simplest case. It is here presented. So you have you can model in such way. You can model both because you have the motion of a magnet. So you need to have some motion of a body, and this body should be also magnetized. So then, if you have moving magnet, you have a variable flux in the coil, inside the coil. Yeah, so this is the flux inside the coil, and here you can see such a picture where this is schematic picture, still schematic picture, but you can see the device. So the mass is in fact magnetized like in previous picture, but now you can see that the flux is moving. So you have to if you have coil, the coil is somewhere here presented. So the mass should move in such amplitude that you have considerable change of the flux. Because if it is totally inside the coil, then maybe flux is still the same. Yeah, you see, but it should. The best is if a magnet is going outside the coil, outside and going inside. Yeah, because then there would be difference of a flux which is going through the surface of with respect to the flux orientation, to the coil orientation, and then you can also write this voltage in terms of number of coils and a number of turns, and also the size of the coil, so with L, and the velocity. So you have voltage which is proportional to velocity, and then you can have such a efficient harvesting. So you can see that such an installation needs some space because you need some considerable motion of a mass just to go outside the coil and outside and inside. Yeah, so the system could be arranged in different way. For example, Professor Sheikh Farouk Ali mentioned about pendulum. So the pendulum could be the so-called oscillator, mechanical oscillator, which is in fact in our system resonator, because we are also looking for some resonance conditions. So this resonator is an oscillator in resonance conditions, and this is one of the weak points for the energy harvester, linear energy harvester, that we should look for some resonance, and the resonance is like maybe single frequency, which is related to the natural frequency of a mechanical system. So mechanical system is the mass on the spring. If we have such a single natural frequency, then the motion should be in such excited with such a frequency. So the excitation is here on the frame. It is provided to the frame here, and inside the frame there is like a coil is attached to the frame, which is rigid frame, and the mass is moving through the coil. Yeah. So this is the linear system, and this is you can see that this is only some kind of approximation because you can tell that this could be actually non-linear system because it is easy to provide some non-linearity. For example, you can have some stopper of a spring because spring could be excited too much. Usually people are using some additional magnets, and magnetic field is magnetic interaction is nonlinear. So it is easy to build from this linear system. Linear system is that we can design the system and we can approximate by linear formula. Yeah. So this is what we are doing for the first time. However, if the amplitude is not very big, then the system behaves linearly. Because as we discussed yesterday, when nonlinearities always have some kind of higher powers in the restore force. So this is not just proportional to the displacement. The restore force is proportional to some polynomial expressed in the displacement. Yeah. Yeah, I tried to make larger letters, but the screen is small. Yeah, so it's small screen. Yeah. Let me tell that this device is like a basic, and here you have some. This is like a review paper by Wei and Jing. So they have had such a discussion. If somebody is interested, then it is easy to find some source of this discussion. However, if we go to some other schematics, you can see, for example, two separate systems with some coupling. So the coupling is through the coil. Coupling is through the coil. So you have coil, you have mechanical subsystem, and you have electrical subsystem. However, the coil is like a solenoid here in the electrical circuit, and you have also symbolic coupling because this is. In this schematics, it is doubled. So you have so-called electromotive force, and then you have load resistor. And load resistor is important because if you want to transduce the mechanical energy to electrical energy, then we need to have some load because otherwise it is open circuit. Open circuit is simplified system because you don't have actually active circuit, but it is open. So the resistor is very large, so there is no current. So people are also studying open circuit, but open circuit would be simplified, and I will tell you that the equation, one equation is not necessary for the system. So it would be that actually the voltage would follow some flow of some motion of a mass without any resistor which is dissipative. So resistor is dissipative. It is like a damper. It is working like a damper in our mechanical system. So if I go back, you can see that there is a mass, but there is no damper. The damper is provided in this schematics. Damper is actually the electromagnetic coupling is provided by electromagnetic coupling. However, it is a simplified picture, schematic picture, but there is for sure there is some small damping. Even if you have a spring, you have some materials, damping. So material of a spring. It is plotted here. K is like a stiffness coefficient for the mechanical system. However, the additional damping would be provided by the electromagnetic coupling to the mechanical system, and this is like a coil. In this way, it is coil, because coil is capturing the magnetic flux, and my magnetic flux is changing, is variable in time. Yeah, so this is the Faraday law for electromagnetism, and then if you look to that system, you can derive some equations, and these equations I follow some equations which were provided in this Mann paper. So this was done in 2012. In this paper, they provided some derivation of equations, and in this system you need to find what is the kinetic energy and what is the potential energy. And of course, there is some additional dissipative. It's a dissipative term which is written here. Which should be divided by 2 as well. So there is some dissipative term, and you have also some coupling. The coupling should be considered carefully. However, in the coupled systems, you can look also what is the generalized variable, and what is the force which is. Please come in. What is the force and what is the work made by the in terms of generalized variable. So you have some generalized force, and when you can look for these forces as in our system are just couplings, and if you have kinetic energy and potential energy U, you can derive the equation of motion. Yeah, so I'm not sure if you are familiar with such a procedure, because this is the procedure which is usually presented on the dynamics course, and this is called Lagrange equation. However, Lagrange equation is only a useful way to derive the equation of motion, because you remember, if you have very simple problem, you can always have Newtonian second this is like Newtonian second law. For the dynamics, and then if you have few bodies, it is possible just to look for the forces in the diagram. And free body diagram, and then you can write this equation, but you should remember which force is acting in which direction, and then the problem is coming to be complicated if you, for example, if you have many bodies, or if you have some couplings. So if you have couplings, because you remember that you can just present your energy in different variables, not only in mechanical variables, and this is the Lagrange approach. So Lagrange approach, the equations of the second type. So you start from the energies, and you have some damping force, some damping term, which also like a derivative of a damping term is with respect to the variables velocities. So you have some damping term, and you need to have some coupling. So the coupling is these couplings are just represented by some generalized forces. So the generalized forces are coming to the equations, and here you have equation for mechanical system. This is the linear equation, and this was told by Professor Sheikh Farouk Ali. But all the variables and the derivatives are just in power 1, or it could be 0. Like 0 is like constant, but it is constant can change only the equilibrium point. It is in other way you can tell that this is like a static solution. Static solution is one of the solution of a linear system, and if you have some static, for example, gravity effect, so this is like a static deflection. When you can separate this static deflection, because you shift only the equilibrium point, and you can still work with some on some to find some other variable solutions which are non-trivial. So you can see that we have y is displacement, and if you go back to that system, so this was x here, yeah. So I think I'm using different notations from different papers, but it is y is good, yeah, because y is a relative displacement, yeah. You can look to this system in such way that this is a kind of relative displacement, and you have inertial force. Yeah, inertial force is provided by excitation. So you can also look for this into the equation in such way, and Q is charge. And Q dot would be current. Q dot would be current. So it is possible to use some other variables because you can express energy in different variables. For example, you can think about if you have pendulum, you remember that for the pendulum it is the best to select just the variable which is like an angular variable, but you can start from the Cartesian variables, and then you have to just to substitute by the variable which is the most useful. And even in pendulum, you can still tell that there are more choices, because you can tell that you can describe the system with some variable which is length around the circle, which is made by the center of mass. So you can tell, but this could be also good measure, good variable for the system. So these are generalized variables, and here you can modify this system in such way, for example, that you see that in that equation you have q dot and q dot. Q double dot. So Q dot is like a current. So you can substitute this in this equation by and you can tell that this could be represented in current. It could be also voltage. So I remember that yesterday we discussed similar system with voltage in the equation, but the voltage can be just estimated from the point of our definition. So, for example, we define voltage on the electrical load. So this is like Ohm's law. It's like U times I is it's I times R is U. Yeah. So this is the possibility. If you have current, you can switch to voltage immediately as well. So this is some there is some freedom in selection of variables and in some but here of course it is easier to reduce the derivative. So if we have current, because Q is charge. So if we go to the next point, we can notice that in our system is also related with some parameters, system parameters. But for some calculation, if we want to have a general result, if we want to have some general result, so for example, for any parameters, we provide dimensionless form of the equation, because if we have some dimensionless form, we can tell that it would be possible to go back to the original parameters, and there is another goal for this non-dimensionalization, is that you reduce large and small numbers in calculations. So you can imagine that if we have many operations, numerical operations with small numbers or large numbers, then we can easier make some systematic error from computation, and it is so it is also computation time. So you can be around 1 in calculations. so when it is like quite easy to estimate result, and also shorter computation time if you have such a dimensionless equation. So we have to divide by mass this equation. However, there is also characteristic, if you divide by mass, you have K over M. So this term is also like square of natural frequency, because you can see that if we have such a simple system, and then for the simple system you can imagine that this is like a harmonic solution. So y is equal to some sinus with some omega t, and then you can have, for example, natural oscillation, and when this term which is coming with double dot would produce omega square. Yeah, so omega square. So the natural frequency could appear k over m if you have no other excitation term. Yeah, so please I'm just looking for some places. Maybe there are some places here. Yeah, and there is one chair here. Yeah, one chair here, and some more chairs are. There is also one chair here. Yeah, there's also one chair here. So I mean that if you had such a course on mathematics, you know that this could be solved in some way, such a linear equation, and this is usually solved in such way that there is like a homogeneous equation and the non-homogeneous equation. Homogeneous is without term, and there is another with term. So you have in fact this is also reflection of a rule that you are looking for special and general equation for homogeneous and non-homogeneous equations. But for example, you can tell that there is a solution with omega. If there is such a equation for the just for single variable, you can tell that there is one solution with omega t, and you find this specific solution for non-homogeneous system. And you can tell that in addition to that, there is a solution which is with natural frequency, and it is not affecting the extra term, but it is also the case if you put 0 on the other side. There is also such a solution, because if you add this solution to y, you also satisfy the solution. So there are at least 2 solutions. However, the damping is provided, and the damping would be effective on the natural vibration, because you have no excitation for this natural vibration, so it would be damped. Yeah. So only for this solution it would be such a important solution with a excitation frequency. Yeah. So the solution of a differential equation, linear differential equation, is you can study this in mathematics course, and then it is the reflection of this superposition rule, that if you have in the linear system, if you have different solutions, I told you that there could be also static solution with a changing the equilibrium point. So if you have several solutions, you have the sum of these solutions could be also solution. Yeah. So it is also the solution. So you can find more solutions, and finally the combination of this solution is the most general solution in the linear system. And here I told you that it could be reduced. Some people can enlarge this system in some way. For example, if you add some capacitor to that previous structure, if you add capacitor, for example here, there is only coil, and this is like inductive term, and inductive term is proportional to the current. However, if you add also some capacitor somewhere in the circuit, then you can get also some linear term with a charge. So it's like for the capacitor, you have the voltage would be related to the charge divided by capacity. Yeah. So, but this is not present in that system. But it could be present. I would tell you on the on the next days, we would also have some session on the developments and future perspectives. So the power electronics is also important to that system, I would tell. And here it is the simplest. It is the simplest way that you have load resistor, and the load resistor is your simplest load. But in fact, if you want to have to optimize the power output, you need some power electronics. And in the power electronics, the simplest device is rectification. So you rectify the current just to charge the battery, because otherwise charging battery is not possible. And the charging of battery is one of the important application of these energy harvesters, because it is you know, if you rectify by diode or some similar more advanced electronics, then you can charge battery, but you can lose some energy. But in fact, here we are interested in some direct transduction. So we are not using any specific power electronics, and in some papers you can also look for some different criteria. For example, you can look for how long the battery is needs to be how long needs to be charged. Yeah. So this is some criterion which could be used in some applications. However, we are not just now. We are not looking for that, because we have the main problem with the resonator and transduction. So the electrical circuit is simplified, and the reason to optimize in the power electronics is also that you can imagine that the coupling is in both sides. So you have, for example, electrical part and mechanical part, and the coupling is in both sides. So you have the flow of energy in both sides. But the power electronics is also working to rectify the flow of energy. So you want to capture the energy in the electrical part, and you want to keep this energy in this electrical part. Yeah. So this is this could be more advanced electronics, which is going to do. But for the time being, we are thinking about the resonator. But could be capacitor, because I think capacitor is a little bit. Could have different reasons. Just the application of capacitor could have different reasons, because you can imagine that capacitor could be useful if you have, for example, charging of battery. Yeah. Then you can have some kind of a parallel capacitor, and then this parallel capacitor or supercapacitor can also work like a battery. So when you need to rectify and make some other changes just to use this capacitor. But there is another reason that you can use the capacitor also here, because you have current is flowing through the capacitor, no problem, because you have variable current as a solution, and then you can tell that capacitor could provide second frequency, natural frequency, because you would have two variables, not only one which is mechanical, but also Q would have full representation, just Q double dot, Q dot, and Q without dot, and this would be another full oscillator. So you would have two frequencies, two natural frequencies, and you can manipulate with two frequencies just to have broadband. For such for some reason, it could be useful. Yeah, but it is not done here. Yeah, but I will show you some other examples where this was used. That we have additional frequency, natural frequency from the electrical system. Yeah. Yeah. And some in the piezoelectric system, it is other way. When we have capacitor already, but we sometimes we add inductor like a solenoid or coil, yeah, to the system. Yeah, so this is for the same reason. But this is not the basic structure. It's not the basic structure, but it is like a more advanced structure with some additional electronics. But this is the simplest way. And I told you that we reduce the system to dimensionless. So just to improve our calculation, we have less error, and we have also so we have smaller error of calculation, and we have faster calculation. If we are doing with numbers around 1, not for example 10,000, not 10,000 or very small like 1 over 1,000, but it is just around 1. Yeah, so we have these variables. You see, but this could be, this is one missing point. Yeah, this should be also plus y. So I'm sorry for some missing points. Yeah, and then we are looking for some solution. And if you have such a linear coupled oscillator, you can think that the solution could be like that. So this eta is also new. It's a new frequency, dimensionless frequency, where and also tau is dimensionless time. Time dimensionless time. It is estimated from omega. This is the excitation frequency and natural frequency. So from this ratio, this is dimensionless frequency. Yeah. So eta is dimensionless frequency, and also you have dimensionless time. So you have eta is when it's around 1, because we are close to the resonance, and the resonance is present if omega is equal to if large omega is equal to small omega. So this eta is around 1. So it's easier for us, because it could be sometimes very large or very small frequency. But I would also tell that dimensionless equation is very useful for nonlinear systems. So it is no other way to study nonlinear systems. We need to use some kind of we need to apply some simple rules like harmonic balance, or maybe small parameters expansion, and then we should be close to the linear system, or linearize we should linearize the equation and look for some small nonlinear parameter. Yeah. So this is our solution, and our solution is that we can have the same frequency, but it could be different phase. Could be different phase. So the phase is you see that the frequency is the same, because we have eta everywhere, but the current is a current and displacement. This is the relative displacement, and when you see that this constant A, B are different than C, D in general. So if they are the same, then you can have the same phase. Usually, the same phase is going to appear if you have, for example, no damping. Yeah, no damping. Yeah. But we have some damping, so there is a shift in phase in these equations. And this is the solution. So, I would tell you that this is one of the possibility that you predict the solution. You predict the solution, and you substitute to the equation this predicted solution, and you calculate the constants. So it is one of the possible way to find the solution. The other possibility is to make the Laplace transform. Yeah, so you have Laplace or Fourier transform. So this is like a transform which is going from the time domain to frequency domain, and this is possible to do the transformation because you have only power 1 in the equation. So this is like a power 1, power 1, power 1. So you can easily calculate the transformation of a single variable to the for example Laplace domain. Laplace domain is a little bit like frequency domain. However, it is more general. So if you go to the Fourier transform, you can also make Fourier transform in a similar way, and you can get frequency domain. So this can be done for single variable, but if you have variable to some power, then there is a problem because it is complicated transform, and you need some additional computational time, and this is however sometimes this is done, and in the MATLAB you can do some there is a Simulink, this is like toolbox, a Simulink toolbox, and then in the Simulink toolbox, the application is through Laplace transform. So you can do this, but you need some to solve some other problems with complicated transform of a higher, or in the higher order if you have squares somewhere, but it is linear. So for linear, it is easier to substitute. It is also easy to calculate some kind of transforms. In nonlinear systems, it is better to stop with a transform unless you have maybe Simulink. So Simulink is like numerical, and in nonlinear system, you rather make some substitutions like that, but this is like your prediction. So the prediction is important in the nonlinear systems, but you can easily go from linear system to nonlinear. Yeah, so you can control the process just adding some nonlinear terms in the equation. So here there is a power, and the power is expressed analytically. You can also calculate in numerical way, just solving like it was presented yesterday, the MATLAB code with some Runge-Kutta approach, or Range-Kutta. So this is depending on the spelling. So when the power is proportional to this the square of amplitude, mechanical amplitude. Yeah. So the power is in terms of a current square times resistor. Yeah, resistivity R. And this is like rho. Rho is used because these are dimensionless parameters. Yeah, but if you know such a result, you can go back with substitution, and so with these are parameters. You know this how it was substituted, so you can substitute back to the that all these parameters, and you can see that this is possible in both ways because we have linear system. We have linear system, and it's a easy task. However, some parameters could be also squared. For example, if you have variable to some power, then if you scale the variable by multiplying it, so the square would be multiplied by the square. So it is not so easy for nonlinear system just to look for the scaling, but the problem is that we should anyway we should for calculation reasons it is better to use dimensionless equation, and when I would go to the results, these are the results from this Mann paper, like Brian Mann from US. So this was one of the early papers, 2012. So he provided such results. For example, if you look for the response, like voltage, so voltage is it's also around 1 because dimensionless units, I'm not sure if it is voltage or vibration, mechanical, the oscillation amplitude, mechanical system. So this is oscillation amplitude, and this is the dimensionless frequency. So this is around 1, yeah, because 1 it is you have such a dimensionless equation. So I told you that all important effects are around 1. So you have increase at 1, and this is this eta is dimensionless frequency. So you have matching of the frequencies, natural frequency and the excitation frequency 1. So this is the amplitude versus frequency. And the power is also following the same way. You have only one frequency, and only for this frequency the power has a satisfactory level. Yeah, but if you are away, then it is not very good. So it is difficult for energy harvesting because. This was maybe also mentioned by Professor Sheikh Farouk Ali, that we are going to harvest energy from ambient conditions. So we don't know actually what is the frequency. We can predict that the frequency is changing with in some range. Yeah. But it is not fixed. Ambient conditions is that this is not fixed frequency. So it is not very good way to harvest energy in such a linear, because we need some control, and the control to cost some energy. But there is such a control, and maybe I would show you some example. Tomorrow there would be some continuation on nonlinear dynamics, but also for linear system there is such a procedure, and this is like you control the resistor. Yeah, so there is such a possibility that you can look for the optimum resistor, but you need some power electronics, because if you have a constant resistor, then it is not working. But if you control resistance, for example, by some electronics, which is looking for the frequency or something like that. So it is sensitive to the frequency when you can apply such a system, and this is also provided, such a solution. But you have some. This is called tracking maximum power, and you change resistivity or some similar approach can be done, because there are many versions of that maximum power tracking, but it is possible to do. However, it is not such efficient as nonlinearity, because nonlinearity could be just present, and when you smear a little bit with single frequency to some larger band. So if you have piezoelectric system, you usually speak about this PZT. So this is like a lead zirconate titanate oxygen. Yeah. So this is PZT, and this was told by Professor Sheikh Farouk Ali, that you have some reorganization of the charges inside material. So if you provide some deformation, then you deform the material in a global way, but there is some internal change of positions of ions. This is important, that this material is usually it is insulator. It is insulator, and it is based on the ionic, couplings. Yeah, so this is like ionic couplings, and these couplings without any pressure, it would be, or without any deformation, it would be some specific, distribution of these ions, and if you provide some deformation, then you can change this distribution, but for application, it is changed by small amount. It is not a completely changed, because this material, piezoelectric, is also so-called ferroelectric. Ferroelectric material is like similar to ferromagnetic. You have in magnetism, you have some ferromagnetic, so diamagnetic, and here you have some ferroelectric and dielectric. And there was a question yesterday about the temperature. So the temperature, there is such a temperature. Also for magnetic systems, there is a Curie temperature, and the Curie temperature is also for ferroelectrics, but for ferroelectrics is pretty high, like over 200 degrees Celsius. So if you have such a temperature, when you lose ferroelectric properties, when piezoelectric is not working, because piezoelectric should be ferroelectric. So I think most of or maybe all the piezoelectrics are ferroelectrics, and they have domains. So the domains, like ferromagnetic domains, they can be oriented, and in application, these domains are oriented, and we are calling this polarized. This is like a polarized and polarization procedure. There is such a interesting procedure that you put material which is to the very high temperature in the oil, yeah, and you provide the electrodes to polarize, and it is easier to polarize above Curie temperature, and if you cool the system, you would get finally the polarized piezoelectric. And the polarized piezoelectric, if it is deformed, it is changing in small in small amount the distribution of ions, but there is a it's very regular, so it is a crystallic or polycrystal, but still you have the same domains. So this crystallic structure is giving you larger response, because this is polarized in the same way, and you change this polarization with some small amount, but if you estimate in the whole crystal would be summed, or all these changes would be summed, and then you can finally have some voltage like around few volts for device, or maybe it would be even 100 volts, but it is not some. Usually this is like few volts on the piezoelectric which we have in a laboratory. So the problem is that usually we design such piezoelectric in the form of a beam, elastic beam, and we are using this mode 3-1 because you have this is the how you measure the voltage. Voltage could be measured in the direction of a force, compression or extension, or you have perpendicular direction. So we are using this 3-1 mode for the beam, and during the deflection there is some. If you consider the layer, a single layer, it would be extended. So like this one mode, yeah. So you can have electrodes on the top and bottom, and you can measure the difference. And the electromotive force is inside the material here. So in electromagnetic system was inside the coil. Here it is inside the material. And the problem is that this is also, it is continuous system. This is the other problem. And in general, we need to solve this continuous body by partial derivative equation, as it was mentioned yesterday. And we have also some tools, so I would try to show you some example how this is solved with piezoelectric and the mechanical substrate. It could be also the case that you have a monolayer or 2 layers of piezoelectric. If you have 2 layers, then you can imagine that you have different polarization on the 2 layers. So one is extended and one is contracted. If you have such a motion up and down, yeah. So when this is quite efficient, because in equilibrium there is no polarization, no resultant polarization. So in this way, you can derive in the similar way. You can derive equations using these Lagrange equations or some similar approach for the. But this equation is you should remember that this is like a single mode, because you have more modes in the continuous body. You have this is related to the deflection. So if you have only the single deflection in one down or up, then in one direction, then it is like a first mode. But you can have multiple deflection, and this is like a higher mode. And I would tell that here you have capacity. It's like a CP is like a capacity of electrodes. Because if you have piezoelectric, then piezoelectric is usually it is like an insulator. But you have the circuit. The circuit could be like a variable circuit. Could go through the capacitor, and inside the capacitor is piezoelectric, which is changing the with the shape. It's changing the shape, and from the changing of the shape, there is some additional polarization, change of polarization inside the capacitor, and it is attracting some charge to be circulated in the circuit, electrical circuit. So this is. And here you have something like open circuit, but usually we have a resistor, because I told you that the resistor is changing the power, because if you don't have resistor, you have no power, because electrical power is like voltage times current. If there is no current, no power. so you need to put some resistor, and if here it is divided by resistor, so it's difficult to tell. But this is after manipulation of the equation. Yeah. So resistor was at first multiplying the two terms, and then you see that with resistor 0 is not useful. The second equation is not useful. Yeah. So you need to have some resistivity to get the power, and also this equation is important for that case. So this is again similar to the electromagnetic. You have a restore force. Restore force could be just linear, but it could be also nonlinear. So here we are talking about linear solution. And you know, these two equations are quite similar. Yeah, there is restore force, which is not written here because there is like error. Yeah, but I will correct this error and give you this also this presentation just to your individual study. And there are some references inside. So the last point is this is from the paper by Erturk, Alper Erturk from US. So he this is maybe in 2016. The reference I would provide also reference for that in your materials. But you see that he studied the continuous body, and this is like a power output, and you have the first mode, second mode, and the third mode. So you see that this is a huge difference, because the first mode is about I'm not sure, but this is like maybe 30 hertz, but the second mode is more than 300 hertz. Yeah, so this is a large difference between the modes. So if you pull this rigorously, this was solved with Euler-Bernoulli approach. Euler-Bernoulli is enough for such system. But you can use also finite elements, and you can confirm the solution. And the third mode is like 800 hertz. Yeah, so this is very large frequency. So this is why we can do such approximation, but we are interested only in some small frequency, like range, like maybe up to some 50 hertz, but not more. Yeah, not such 300 or 800. Yeah, so this is the case. Yeah, yeah.
Frequency comes from the mechanical system.
This is mechanical. Yeah, yeah.
Resistance comes from electrical part, load resistance.
Electrical part could be also if you have. I told you, but if you provide some more advanced power electronics, you can also have some electrical parts. So resonance in electrical system, yeah. But this is not. It's not done.
By changing the resistance.
Yeah. The resistance could be changed, but this is only small change on this graph. You see, but this is like resistivity is changing for different curves, different colors. Yeah, so it is changing, but not so much. So you are right, but this is mechanical part is dominating here, and we don't have any electronics, power electronics, only resistor here. Yeah, so no other peaks, no other peaks. Yeah, but if we make some power electronics, maybe it is improving a little bit. However, it is one can tell, but in the linear part it is easy to predict, but in nonlinear it is difficult to predict. But you can in nonlinear systems you can predict some qualitative changes. Yeah. So the quantitative is not so easy because you need to calculate to check if it is large effect or small effect. Yeah. Okay. Okay. So I just want to finish the first part of this of today presentation. Yeah. So maybe questions. Yeah.
Can you go back to slide 8?
Yeah.
Slide
8. Yeah. Okay. This 3-1 mode, yeah, 3-1 mode, yeah, because this is like extension, but you have some deformation like a delta. It's extension and contraction on the lower part. Yeah, so you can provide either two layers which are polarized in different directions. So, for example, if you have some polarization which is going down and this is going up, there would be different effect on both of these, and they would be summed even. Yeah, so you have even larger effect than the single layer. This could be made only by piezoelectric, but there is a problem. If you have only piezoelectric, maybe to some small size device it is okay, but it would be very brittle. I think if it is only piezoelectric, it is very brittle. It's better to have some substrate of a metallic part. Yeah, so something like that. Yeah. So, or maybe some other material, but it is depending on your aim. Yeah. This is also I think that this free is also used for excitation. So you can excite in exactly in the same direction, and this could be also used for energy harvesting. But we are talking about such a configuration with a beam, so it's better to use 3-1. It was checked that the 3-1 is better for the beam application. Yeah. But if you have if you have different system, but you have only a possibility to move in one direction, when you apply because this is like a two-dimensional motion. Yeah, but if you have only single dimension, when you apply this free mode, yeah, so you make some kind of excitation. Excitation is probably with actuators. Yeah, so actuators are just provided by such a free mode, and I think maybe also with accelerometers. Yeah, accelerometers maybe they are also using some mode like free. Yeah. Yeah, this free mode is. I told that this is for maybe for actuation. It's made for is good for actuation. However, I would tell that the efficiency is dependent on the coupling. Yeah, so the coupling is better for this 3-1 mode. Yeah, so this is very higher coupling. So higher coupling is one point, but so I was not, some years ago, I was thinking that efficiency is the same as effectiveness, but this is different, these are different words. So efficiency is related to the materials property, and the effectiveness is related to the structure. So we are telling that, for example, we can make some different structure, non-linear structure, and we can improve effectiveness of the system. But the efficiency, which is is based on material coupling, on the coupling. Yeah. So we cannot make a large change, and this is possible to make smaller and smaller such system. However, if you have electromagnetic, then there was some size was involved in this coupling coefficient. This is like a voltage and velocity. So this is like a mechanical velocity and the electric voltage. These are related with some number of turns in the coil, and this is like B is a magnetic field, but also L is the size of a coil. Yeah, so the size of a coil, this is like approximate, this is approximate, it's approximate, formula here. Yeah, because usually this L is like a long straight line, yeah, and you can move by this line, yeah, but it is and you can easily calculate the square of the shape is like a square, but this is like a coil is like a circular shape, yeah. But approximately is like L, yeah. Efficient, I mean, this coupling is important, and if you make smaller and smaller, you have smaller coupling. Yeah, so this is the problem with the expansion of this flux. So you cannot scale down. So if you have enough space, then maybe electromagnetic is more stable, because piezoelectric can have some cracks, so could be damaged easier. But there is some you would learn in the laboratory that there is some composite, piezoelectric composite, which is more flexible. Yeah, so it is specially made such a PZT composite, which is more flexible, that you avoid damage to that system. Yeah.